Okay, so we have just said that so the eigenvalues in finite dimensions are the roots of the characteristic equations. If you're in infinite dimension, we will take some examples later on. You will see that we need to go back to the definition of eigenvalue. However, so in finite dimension, um, you get the characteristic equation, you get its roots. It's a polynomial of degree n, so you know it has some roots. These roots can have an order of multiplicity greater or equal to 1, meaning you have a double root if you can factor by this root twice, and so on, okay? And so the multiplicity of this root, this is something you know for the roots of a polynomial. And so the dimension of the associated eigenspace is always going to be, well, greater or equal to 1, at least 1, and smaller or equal to the multiplicity of the eigenvalue. It's not very complicated to show, but let's say it's just it relies on the fact that if you can diagonalize, if you can express this matrix representing your map in a basis that is made of a basis of E lambda, and you complete this basis that's come from the incomplete basis theorem that we saw at the beginning of the chapter 3. You can complete this basis with the basis of E, and then if you know that the determinant of the matrices don't depend on the on the basis where you're at. Why? Basically because you do your change of basis by multiplying by some passage matrix and also multiplying by the inverse of the passage matrix, and the determinant of a product of matrices is the product of the determinant. The determinant of the inverse matrix is the inverse of the determinant of the matrix. So in the end, you always get the same kind of determinant no matter what the basis you're looking at, so that if it's a root of size of multiplicity of m in some basis, it's still going to be a root of the same multiplicity in another basis for the determinant, and so well. However, you can show that the dimension of the eigenspace is at most equal to the multiplicity of the eigenvalue, and one first consequence is that if you have a single root of the characteristic equation, the dimension of the associated eigenspace is 1. Okay. And then finally, we've got this very, very important theorem that f is going to be diagonalizable. Basically, if you can find enough independent eigenvectors in order to make a basis, in order to change your basis to represent f as a diagonal matrix. Okay, and so it's going to be diagonalizable if if summing all the dimensions of the eigenspaces, you get the dimension of the space, right? That's basically what it means, right? Adding, that's what is written here. Adding the basis of all the eigenspaces makes a basis of E. So it contains all the eigenvectors, okay? So you need enough independent eigenvectors. It means that if you only have n roots, let's say n real roots that are distinct, no problem. You're going to get n independent eigenvectors, because we already showed that eigenspaces make a direction. Now the problem comes when you have multiple roots. So what you should remember, when you have multiple roots, when you have a root of multiplicity m lambda, you need the dimension of the eigenspace to be equal to m lambda in order to make the diagonalization possible. Okay, you have to have enough independent vectors that make a basis of the corresponding eigenspace, in order so that in the end, if you take all these vectors of the let's say eigenbasis, you will get a basis of the whole you will get enough v eigenvectors v lambda 1 up to v lambda n. You have enough of these in order to make a change of basis matrix. Okay, that's it. All right, and you have this is just we already saw why your matrix would be expressed as a diagonal matrix. We saw that in that example. You remember, you f of v lambda 1 is equal to lambda 1 v lambda 1 and so on. You get this diagonalization possible, right? And so what you need in order to do that, you need this to be a basis. If it's not a basis, you can't have this representation. So you need this to be a basis. And the change, what's the relation between your previous matrix, let's say M was the representing matrix of F, and this one, it's a change of basis representation, P, D, P minus 1, okay? M is equal to P, D, P minus 1, or sorry, if I use Mr. Biles' notation, and maybe common notations, your diagonal matrix is called with the capital lambda, and maybe you get sigma and sigma minus 1. All right, yeah. I don't remember exactly the notations that are used, but let's say this, you have to remember one way or the other, and in here you've got the columns of P or the eigenvectors. Okay, so in order for P to be invertible, well, so P minus 1 exists, so you can write this change of basis formula. So you need P minus 1. Of course, you need all these eigenvectors to be linearly independent. You need enough of those to make a basis. Okay, so that's it, right? So that's the final formula. Okay, finally, maybe let's do, I'm not going to do some simple examples with matrices now. Maybe we can try an infinite dimension example. Okay, so that's a nice one. Let's consider the map D, which is going to give you the derivative. So first, let's consider it in the space of polynomials. Okay, polynomials of any degree. So that it takes P and gives you P prime. Let's find the spectrum of D. Okay, so we've already showed several times that this was a well-defined linear map, and so the spectrum of D. I'm looking. So I've got an infinite dimensional space. Okay, so I can't use the usual techniques of diagonalization, and I must go back to the definition. I'm looking for lambda such that there exists non-zero P with D applied to P is equal to lambda times P. Okay, let's see what it means. D applied to P is actually going to be equal to P prime is equal to lambda times P, right? And P has to be different from 0. So first consideration, we say that, well, if lambda is different from 0, what do we get? On this side, we get a polynomial, let's say, if we started with P of degree of degree n, we get a polynomial of degree n, and when we take the derivative, we get the polynomial of degree n minus 1. So there's no way that these two polynomials are equal to each other, so no possibility here. We have no possibility. We have no solution to this kind of thing. All right, so we got no non-zero eigenvalues, but let's consider if lambda is equal to 0. Can I find P prime is equal to 0? Yes, non-zero p such that p prime is equal to 0, yes, we take p is equal to constant. Okay, and actually this we already knew because maybe I haven't stressed that enough. Lambda is equal to 0 corresponds to the null space, to the kernel, okay, kernel of the map. So if the map has a non-zero kernel, it means that it has eigenvalue equal to 0. So the spectrum of D in that case is just the 0 eigenvalue and 0 eigenvalue, and the eigenspace associated to that 0 eigenvalue is going to be spanned by it's any constant, so spanned by the polynomial 1. Okay, for instance. All right. Now let's consider the same map D, but from C infinite functions to C infinite functions. Okay, functions indefinitely differentiable. Right, so that for any function it associates its derivative. Same questions, what are the eigenvalues? Okay, and so we are in infinite dimensional space, so we can't work on any matrix representation, but let's see what it means to have an eigenvalue. Lambda is an eigenvalue of D. It means that there exists f different from the 0 function such that df is equal to lambda. So let's try this. Assume we've got something that solves that. What does it mean? So f prime is equal to lambda times f. Well, actually, I know how to solve that in the space of infinitely differentiable functions. Okay, that's just the differential equation f prime over f is equal to lambda, and you know that you can solve that by, well, we integrate, that gives us lambda f is equal to lambda x plus constant. We take the exponential, and we get that f is equal to any constant times an arbitrary constant times e lambda x. Oh, good. Right. How can we interpret this? Well, it's a very nice result. It tells us that for any real value lambda, we can find non-zero function f equals to f of x equals to c times exponential of lambda x, such that t applied to f is equal to lambda times f. Okay, that's what we said. So what does it mean? It means, first of all, that the spectrum of my map D is actually equal to R. For any real value, I can find the corresponding non-zero eigenvector, okay, eigenfunction in that case. And what is the eigenspace associated to any eigenvalue lambda? Well, you see, this writing c times exponential lambda x is just to say that any function that satisfies this equation is collinear to the e lambda x function. Okay, all right. Okay, so the eigenspace is, we've got an infinity of eigenspaces, an uncountable infinite number of eigenspaces, because it corresponds to all the real values. All the real lambda will have a corresponding eigenspace. Okay, that was, I think, a very nice example. That has quite a few implications, actually, in terms of Fourier transform and things like this that you can see next year. But you see, it means that we will actually be able to make some kind of basis out of those functions. All right, we will be able to make some kind of infinite dimensional basis for functions. That's quite a nice result.